at the outset, it's probably good to think about a couple of common reaction mechanisms with this carbonyl group here. And this hopefully will save some time and organization later on. So let's think about those types of species of a reaction, maybe where we do not have a good leaving group. So we can consider some generic reaction. Let's just take some generic aldehyde that looks like this, and let's have a nucleophile attack it. Okay, so we're going to have some generic nucleophile, and we're going to fill that nucleophile in later on actually with an organometallic reagent. Now, in terms of the reaction, and we're going to draw this probably 1,000 times in the next couple of weeks, we said that this carbonyl group has a dipole. Oxygen is more electronegative than the carbon, which means that this carbon here, the bottom that I'm pointing to, is going to be electrophilic. So the very common mechanism we're going to be seeing is the nucleophile attacks the electrophile. So we can have the nucleophile attack our electrophilic carbon. However, if that were the only thing that would happen, we'd have 5 bonds on carbon. That's not going to happen. But what we can do is move these electrons up onto this oxygen. Now, actually, if we drew the other resonance structure here, where we already have the negative charge up on the oxygen, we'll be going to the end product that we're going to see. I'm not sure if that actually makes sense, but so let's see what we're going to get. So we'll have our R group, hydrogen. We'll just we formed a new bond with our nucleophile down here. We had an oxygen at a double bond, which now let's put in the lone pairs on the left. 2 now has 3 lone pairs. O minus, as some species. And then now what we'll see is we do not have a good leaving group here. And so in the end, what we'll see in a lot of these reactions is we're going to have water around. We'll either add water to the reaction, water or a little bit of acid. And so what we'll end up doing is we're going to protonate this. And by this, I mean that negatively charged oxygen. So this is all the same. OH, and to balance, let's say that's OH minus. Maybe that was our nucleophile, sodium hydroxide. All right, so now let's use this reaction to get a couple of more details about this. Is that we said that we started off with an sp2 hybridized carbonyl group. We're going to see here that now this middle species, it's sp3 hybridized. This is a tetrahedral intermediate. And then our final reaction here, species, is sp3 hybridized, tetrahedral. Okay. And so now what you'll have noticed is, I'll put it up in the corner here, we've added a nucleophile. So it's nucleophilic addition. I could say to a carbonyl group. Let's try to scribble that in. This is going to be a very common reaction that we're going to see. And for those interested in biochemistry, this is a very common reaction that we're going to see in biochemistry as well. Carbonyl group chemistry is a cornerstone of biochemical reactions. You may have seen it in certain metabolism coverage that you've already looked at. Okay, so now let's look at one more general reaction here. Let's say we have a potential leaving group. Try to leave that so you can compare. And we're going to revisit these reactions with more detail. Let's just put a chloro group there. It's a good leaving group. Now, let's have our nucleophile here. So same thing as before. We have this sp2 hybridized carbon. There's a dipole. We could even draw the other resonance structure. That, if we wanted to help better show that, we'll stick with red. Let's have our nucleophile attack. Cannot have 5 bonds to the carbon. Move these electrons up onto this oxygen. And again, it's supposed to be an arrow. I'll start over. Let's draw a tetrahedral intermediate. So now we have a chloro. O minus, just put the electrons in there. Our nucleophile that attacked is shown here. And now the difference here is one, so let's use blue to try to set that up. Here, I'm going to point back to the top. This hydrogen, we'll say that's a bad leaving group. And try to squeeze it out, I'll just put Lg for a leaving group. The difference is that here with the chloro, we actually have a good leaving group. And this is going to be a very common trend for a lot of reactions. We'll want to ask, when we form this tetrahedral, sp3, hybridized tetrahedral intermediate, we want to ask, now, do we have a leaving group or not? Is it a good leaving group? If the answer is no, like the top reaction, then a lot of times we're going to essentially be stuck. That'll be the end of the reaction. We're just going to go ahead and protonate this hydroxyl group to end up with an alcohol. And notice here we went from an aldehyde to the left to an alcohol, which we added our nucleophile. However, now if we have a potential leaving group and indeed a good leaving group, let's have the leaving group leave. And what we'll see in the many common reaction mechanisms is we're going to reform the carbonyl group. It's energetically favorable, actually, to reform that carbonyl group. And we're going to kick the leaving group out. So the leaving group does as it should, it leaves. And now what we've done is we've taken and we reformed our carbonyl group, C double bond O, with what was the nucleophile attached. We'll use that same language, plus Cl minus, our leaving group. So in this case, we've gone from sp2 hybridized acyl chloride on the left to our sp3 hybridized tetrahedral intermediate in the middle. And we reformed the carbonyl group back to an sp2 hybridized species. I'll say with that color. So now this is going to be nucleophilic. It's addition, elimination to a carbonyl group, and I didn't save enough space, to a carbonyl group, sometimes known as nucleophilic acyl substitution. I don't expect us to memorize those names, just so you're familiar with some of the language. So hopefully this will continue to make more sense as we go through these reactions, as we actually use real nucleophiles, for example. But I want to set up here looking at the trends and notice the similarities and the differences. So here, just to recap, on the top, we have a carbonyl species. Let's put the name there so you can see it. We have an aldehyde. And on the bottom, we have an acyl chloride. Both contain a carbonyl. They're both carbonyl-containing functional groups. And in both these cases, we have this generic nucleophile, top one and the bottom one. So we're thinking about the nucleophile attacking the electrophile, which happens to be the carbonyl group. And that's the same in both generic reactions. Then we form this tetrahedral intermediate, which is the same in both reactions. So tetrahedral, negative charges up here in the oxygen, negative charges on the oxygen. The difference, though, is in the aldehyde, we do not have a good leaving group. So we're simply going to protonate, and we've added our nucleophile. However, in this case, in the bottom, we have chloride that's a good leaving group. So we can actually check that out, reforming the carbonyl group. And so we've then carried out addition, first step, followed by elimination, which is loss of the leaving group. And we reform the carbonyl group. Now, a question that may come up is, okay, you form the carbonyl group, can you have another nucleophile attack here? And indeed, you actually can, and we're going to see that in certain cases. Okay, so those are our two generic reactions. We're going to add a couple of other components to that later on under conditions with weak nucleophiles. The one last thing to mention with this, and this is a picky thing, but it's actually really important, is to think about formal charges in these reactions. You saw that with the first semester. We're going to see that again throughout our discussion here. Is always to make sure that formal charges make sense, because if they don't, there's something that's up in the reaction. And what I mean by that is a lot of times with these nucleophiles, we'll assert this is a strong nucleophile. Formal charges are not created or destroyed, but they're moved around. And so they should balance. So notice we start here with a negative formal charge on the left, negative formal charge in the middle, negative formal charge on the right. Same thing for the bottom reaction. It's negative, negative here, and then negative on the chloride over here. If all of a sudden a bunch of positive formal charges showed up that didn't balance, something's not right. So that's a quick way to check to see if the mechanism is making sense, to make sure the formal charge is balanced. Okay, so I know we're throwing a lot of information at everyone. Hopefully everyone's still at least partially awake, thinking about this. Those are going to be our generic mechanisms. Should we move on?